Hello everyone. In this video, we are going to talk about chapter 15, section 15.5 through 15.7. We're going to learn about the kinetics of a particle, but today we're focused on impulse and momentum. Um, so the angular portions of it. Today we're going to focus on the angular impulse and angular momentum. And then, so starting with the angular momentum of the particle about point O, definition is defined as the moment of a particle linear momentum about O. So we have the H here, H0 equals R cross mv, and we can put that in a matrix. The magnitude of H0 is H0z equals mvd. The resultant force acting on the particle is equal to the time rate of change of the particle's linear momentum. Showing the time derivative using the familiar dot notation. So if I put a dot on top of it, it means it's the first derivative with respect to time. So we know that velocity with respect to time, mv, so this is mv is the linear momentum. If I put the dot on top of it, that means it's the first derivative of the linear momentum. That gives me the angular momentum. We can prove that resultant momentum acting on the particle about point O is equal to the time rate of change of the particle's angular momentum about point O, or sigma f m equals r cross f, which would be h dot. Keep going. The same form of equation can be derived for the system of particles. Now, for a system of particles, the moment of these forces of the particle will be written as two forms, external and internal. And we know that internally, the forces will always become in pairs and equal in the magnitude and opposite direction. Then that means, the second term we're looking at the system is usually dropped because they will be equal on the magnitude, opposite on direction. So overall, consider the relationship between moment and the time rate of change of angular momentum. You have sigma m equals derivative of h dot, that will be dh dt. Integrate between the time interval, we got this equation right here. This is very similar to, I mean, the idea is the same similar to the equation, several equations that we look in the past. So basically, equation refers to, we give it a name, we'll call it principle of angular impulse and momentum. Second term of the a second term right here over here is, we called it, this term right here is the angular impulse. So angular momentum initial plus the angular impulse gives me the angular momentum final, similar to the energy and the linear momentum equation that we looked in the past. Under the condition that sum of angular momentum acting on the particle or system of particle is zero during that time, that means my initial angular momentum equals my final angular momentum. We are going to look at some examples together. Two examples actually. So I have two identical 10 kilogram spheres attached to the rod. The rod is going to rotate in the plane of the page. The sphere are subjected to tangent force of P equals 10 Newton, and the rod is subject to a moment M equals 80 Newton meter, where T is a second. We're looking for the speed of the sphere at T equals 4 seconds. If the system starts from rest, we know that start from rest means that initial velocity will be a zero. That's putting into our conservation of angular momentum equation. Initial angular momentum plus the angular impulse equals the final angular momentum. Initially, I know velocity, we're starting from rest. We know it's going to be zero. The impulse, angular impulse, we have two of them. This one refers to the 10 Newton. I have 10 Newton multiplied by zero point 0.5 meter, and I have two of them. And over the period of time is zero point 0.4 second. The other one is this M right here. The M that's in the middle, 80 Newton meter over 4 seconds. Okay, integral, both of them. And then right hand side, since I have two of them, that will be mass times velocity times zero point 0.5. Mass times velocity times zero point 0.5. Okay, so the mass is 10 kilogram times velocity, which is what we're looking for. And then we have two of them. So one equation, one unknown, we can solve for the value of the velocity. Hope that helps you. Second problem, it's a group problem here. Normally in the classroom, I will have students do it together. But since this is an online class, we have two 10 kilogram balls attached to the end of the rod. We're going to neglect the weight. We have a torque acting on the rod this much. initial velocity, we look at velocity after 3 seconds. If the ball has a speed, we know the initial velocity this much at t equal to 0. That's my initial velocity. We're looking for the final velocity. Similarly, okay, initial, I have 2 times 0.5 times 10 times 2 because I have two of them. And then final, we don't know the velocity. We'll leave it there just like that. We don't know what that is. We'll leave it there. Okay. And then the moment, angular impulse, not moment, sorry, angular impulse, we're going to take in the integral over a period of time, which is 3 seconds. We're going from 0 second to 3 seconds, 0 second to 3 second, and then plug in this function t squared plus 2 and taking the integral from 0 to 3 second. That gives me 15 Newton meter. Okay, when I apply the principal angular impulse and momentum, you have initial angular momentum plus the angular impulse over a period of time equals my final angular momentum. Again, one equation, one unknown, we can solve for the value of V. Okay, that's what I want to show you in this video. Hope you find this video helpful. Thank you for watching.